All right, guys, welcome. So this should be the very last review session. I mean, on Wednesday evening, because in a week from now we will be done the whole thing. Okay. Now there will be. I thought in class, because you guys we mostly finished the material, right?
Yeah.
There's did you guys get through most of the movies today? I think so.
2 more.
2 more. Okay, but that's fine. You can.
Like the practice.
The practice ones. So guys can just watch that. And then we can go over the solutions together on Friday, and then I'll give you some more problems tomorrow morning. Then we can do kind of an additional problems on Friday. I think that would be helpful, rather than starting something new. All right, it's just practice. And then you guys have the weekend to study for the final, Monday to relax, and then Tuesday to take the final, and then we're done. Okay? Don't study until 4 a.m. right before the final, because you need to be fresh in your mind when you take the final. Okay, so make sure you plan in some time to relax before the final. That's really important. Okay, so who wants to start with the first one? So these are there's certain things, right? As this problem already states, it's very important to realize what not to do. Okay, it's equally important to know what not to do as to know what to do. Okay, so I want you to find the mistakes or kind of the problems with these reactions. Yeah, you want to try the first one? Oops, sorry. It's like a cup from the airplane. It looked like that. Let's see, we can change to... Do
you just want me to say what's wrong, or do you want me also
draw the maybe also draw the one, the correct way to do it, and the way, it's kind of an open-ended problem. There might be multiple things wrong as well. Or maybe show what would form in this case. Okay. Yes, so what is drawn here is anti-Markovnikov, right? And you would form the Markovnikov product.
Yep.
Right? Can you draw the Markovnikov product?
Do you want me to just draw that instead, or do you want me to do the whole mechanism?
Does anybody want us to do the whole mechanism? You guys probably know the mechanism, do you? Or should we do the mechanism?
I do. I want to do the next one.
Oh, you want to do the next one? Okay. So we don't have to do the whole mechanism. You just draw the Markovnikov product. Yes. That's pretty much it. Very good. Let's see, get you
You make a nice trade.
Yeah. All right. So you can do the next one. Okay.
Sweet.
Let me just move on. Does anybody have any questions about this one? Right. Make sure you know the mechanisms. I'm sure you guys all know it. This one. Yes.
Thanks.
You can try. I'll get you an apple. Okay.
Okay. So what's wrong with this is it should be a sin addition, right?
Yes, and it's drawn as an anti-addition.
Yeah.
Right?
So do you want me to draw the correct one?
Yes. Yes.
Okay.
That'll be good. And maybe you can.
Oh my god, I can't draw for shit on this.
It's kind of cool though. It's like a medium-sized iPad.
It's an iPad, yeah.
Sorry, these are not as fresh.
My drawing is really bad. I'm sorry.
No, that's fine. As long as it's clear. Thank you. This is great. So they will take this out and say should be. I'll say should be sin, not anti-addition. Okay. All right. Do you want to do the next one? Let's see. I'll move on to the next one. Here we go. Okay.
So would the ozone have cleaved both?
Yes.
Double bonds?
Yes.
Okay.
That's exactly what will happen. So you can draw the product, what would actually form.
Okay.
Right? So with ozone, you can say, okay, maybe we just add one equivalent of ozone, right? But remember, ozone is a gas. So what people generally do, you have an ozone generator in your hood, and then you bubble the ozone through. And it's really, really difficult to just add exactly one equivalent. Even if you add one equivalent, you're still going to cleave the second double bond as well. So literally, that's what you would perform. And then...
It would be two of them? Or I guess they...
Yeah, it would just be two of them. You could
same.
draw both of them, that's fine. You could simplify it and say two of them, right? Yeah, okay. That's great. So we will say, let me get you an apple. We need to keep some apples for the synthesis problems. Those are the hard ones. Oh, no. It's fine. They still mostly stayed in the bag. I think you guys do you want to take it? Yeah. So what I will say is ozone, right? Oops, let's see. Ozone would cleave all the double bonds, okay? Perfect. Any questions? That makes sense. You just cleave all. Okay? So let's go to the next one. Oh, there's another one. I thought we were done with problem 1. Who wants to try this one? Okay. Oh, sorry. I'm a little jet lagged.
Okay, so I think that this is dashed.
I think so too.
Yeah.
And the other one is solid.
You think it's solid? You don't think it's wedged?
I thought it was wedged.
Oh, okay, good.
Maybe not. Yeah?
No, that's what I thought, but I thought by solid you meant like. Okay.
Yeah, I agree with that.
Yeah.
Because it should be anti, not sin.
Yeah.
All right, let's see. So Caroline thinks we would form this instead. Right. Oh, there's a bit. Sorry, I think there's a little bit wrong.
Oh, that's okay.
Not completely wrong. Actually, people say if you have a worm in an apple, those are the best apples. Because the worm will pick. The worm knows which apples are the best ones. There's no worm in this apple, but I'm just looked. I think it just fell down. So let's see. Do you want to explain a little bit?
So I just.
Just hold it
Yeah.
here so people can hear it in the video.
Yeah, I don't know. I just looked at it and I've been doing a bunch of these and I was like, nope, that's it. But honestly, it was just a gut response.
Okay.
I could try and work through the mechanism.
Yeah, no, it's sin versus anti-addition,
Yeah,
right?
yeah,
so.
so-
First of all, right, you add the BH3, the boron and the hydrogen, right? And remember, they come from the same state, they add at the same time, based on the mechanism we learned. So, and the boron goes to the side where there is the less substituted side, right? So the first thing you form, the first step is BH3, THF, basically you have the BH3 addition, and then you get its sin. Okay, so that means, for example, this is back, the hydrogen here is up, and then the BH3 would be, the BH2 would be back, right? And then next, in the next step, you're going to go, so this particular one would actually give you, you basically just replace the BH2 with OH, right, with the H2O2. It's the oxidation step. And the OH minus, right, the sodium hydroxide. So then what you get, if you see from the one I drew, you would get this thing. Hold on. What did I just, no, you see, this was wrong what I just drew there, right? Because you see the methyl is back, hydrogen is to the front, so the boron must be to the front. In this one.
Yeah.
You guys didn't notice it?
I just nodded.
So you see that was wrong because both it came from the front. The BH3 came from the front, so that means the boron and the hydrogen must be pointing to the front. In the one I drew, okay? So then the methyl is back. We are not drawing the hydrogen anymore. Then the OH is here. All right?
OH grabs onto the H2O2.
Yeah, exactly. But so what you get? You see now I drew the mechanism to get to the enantiomer for the one you drew. So that's the other thing which is wrong with this. You want to draw plus enantiomer. So this is the wrong. This would be anti-addition. This would be anti-addition is wrong, and it should be sin.
No, it is sin. It should be anti.
Well, that depends on the. You mean the product? You mean these two guys are sin, right?
Yeah.
But the addition, you see, because we didn't actually add the methyl group, right? You see, this methyl group was already there in the starting material. So what we actually added is the hydrogen, right, which is in the back. right? Yes, the hydrogen which is in the back, right? You see, and that they are anti. You see, the hydrogen to the OH, those are the two things we added in the two-step mechanism. Those are anti, and that's why I'm saying it's anti here. The addition step was anti, and it should be syn. All right? Does that clarify things? So it's. How would you? One more thing. How would you call the relationship of these substituents? You would call the compound a cis. You would call it a cis compound, right? The product is cis because the methyl and the OH are on the same, pointing on the same side. So it's a cis product, and what we get is what you should get is the trans product. But the addition was syn. Does it make sense? So make sure you can distinguish these terms: cis and trans, E and Z, and syn addition, anti-addition. Right? One is used for the addition, the mechanistic part, and the other is used to characterize the product. One question here, then you next.
Why wouldn't the OH flip up to the third degree carbon, and why it flipped down?
Which OH are you looking at?
So normally when there's a double bond, I thought it when the hydrogen and the OH.
Oh, the Markovnikov versus
So
anti-Markovnikov.
yeah.
So this is correct here as it's drawn because these are all anti-Markovnikov
Okay, so these are
additions.
all okay.
And why? It's a very good question because the way it has something to do with the mechanism.
Okay.
So the mechanism is such that normally when you, for example, have H plus, when you do H3O plus and water, right?
Mm-hmm.
Then the H will first will be attacked by the double bond.
Okay,
You
so
make a
we're gonna be
carbocation,
H
which is, and then the OH comes in, right?
Okay, yeah.
Here it's different. The H and the boron, they're coming in at the same time. But now the H is not the electrophile anymore. But it's not H plus. It's actually more like H minus because it's attached to the boron.
Okay.
The part which is the electrophilic part where the double bond attacks, that's the boron now.
Okay, that makes
And that's why it goes the other way around.
sense. Okay,
Okay, so if you look at the mechanism, it will become clear.
okay, thank you.
But it's very, very important distinction. So this BH3 and then how do we call it? Boration, hydroboration oxidation, I think, is anti-Markovnikov formally in the end. And the other ways we've learned, like the mercuration and demercuration, as well as the H3O plus water, that kind of thing, those steps, they all go Markovnikov. So depending on what reaction sequence you choose, it goes either Markovnikov or anti-Markovnikov, and you have to get that right. And you should understand from the mechanisms why. Okay? That's a very good question, very important. And then the other thing is, again, the syn versus anti, addition selectivity. That changes also depending on reagents we use. Okay? Any other questions? Yeah, you had one. Huh?
You answered it.
Okay.
Oh,
Any
also-
other questions? Yeah, okay.
Can I do the next one too?
Okay, you can do the next one. So let's go to the next one. Let me see. Explain why cis-2-butene provides a different product than trans-2-butene upon dihydroxylation with osmium tetroxide. Draw structures to support your answer. So basically, just draw the starting material in the middle. Do both reactions, right? And show me what products you get, and then that will explain. Oh, let's change the color. Sorry, that was the highlight color. Is it still recording? Okay, that's great. Let's go here and pick black. Maybe let's do red. Let's do black. Right?
Don't get any artistic freedom in here.
If you want another color, you can change it.
No, this is fine. So it's like, and then so
Very big. Why is it so big?
it's thick.
It's very thick. Let's see. Otherwise, you're not gonna get very. Oh,
Yeah.
we should use this one. Sorry.
Pen, yeah.
The pen is better.
Okay,
the
then
other
the
one is
marker.
just very thick. Then you won't see it. All right.
So that's like the cis compound.
That's the cis. Yeah.
And then what you end up with when you have the dehydroxylation, you end up with like two hydrogens on or two oxygens on either side of the double bond.
Yes,
but you
how
kind of
do
get
they
it by
add-
making this
Is it a syn addition or is it an anti?
it's a syn addition because you're making a triangle using the no, wait,
no,
excuse
no,
me,
no,
that's
no,
not
no.
right. Yep.
The
wait.
triangle. How do we make the triangle? The triangle we make with what? With MCPBA, right? Those per acids. That's an epoxidation. This triangle is called an epoxide. That also gives you two OH groups. But if you make the triangle first, the epoxide, right, with MCPBA, and then you open it with acid and water. Then it opens from the backside, so then you got formally an anti-addition. Now in this case, yeah, exactly, you're making this thing, but there's no double bond. Right?
Is there an
Because-
eraser so I don't have to go back and?
Yeah, there is.
Yeah, sorry, I was
We'll do
drawing
it
that
together.
right
That's
on
fine.
what I had.
That's perfectly fine. So this is the eraser. So you see there's no, because initially there is a double bond.
Yeah. I kind of like drew it to be like, oh, that's a cis compound, and then I started drawing what it was going to without
Yeah.
fixing.
So
what
that's what
happened.
you get, right? Because you remember the double bond, the electrons on the double bond, they will attack the osmium or the oxygen.
Do you
of
want me
the
to show
osmium.
the first step?
Yeah,
the
let's do it.
mechanism?
Let me actually.
Okay, sorry.
Let me do it. We can just move what we can do because I'm good at moving the things around here, so we don't have to draw it all again. Okay. So what we're going to do is this is the product of the first step, right? So we're going to move this over here, and then we can select it, or then we just draw the cis product, right? And the mechanism.
It's like a kind of a cyclical, just three arrows.
Exactly, this cyclical thing, right? This one,
The double bond
and
goes
then
to
you
one
can draw this one. Okay. So I recommend when I studied this kind of orgo stuff when I was in your shoes, I would like every time when I would like study a reaction, like with flashcards and stuff like that, I would also write down the mechanism. You know, you need to be super good at doing these mechanisms. It will help you remember much better. All right?
Next step.
What's happening?
So
The next step, you don't need to.
We
do
didn't
the
really- yeah.
mechanism. You just
So
like
then
you
it's
just
just
cleave
like-
it off. I don't remember what do we use to cleave it. Somebody used
Na.
it. Sodium sulfide. Yeah.
So that's what you have for the cis, and then
Yes.
for
more
trans.
like Trans. Yeah. Does this have an enantiomer?
Oh, because it's if you do it with the in the back, you just turn it around and it's the same thing.
Yes. So this is a
So
meso
it's a meso.
compact. So write meso below. The cis one gives you the meso compact, so you don't have to say plus enantiomer, right? That would be wrong. It doesn't have an enantiomer. But now the trans one, I think, gives you a chiral one, so then you need to draw the enantiomer too.
Okay, so the double bond grabs onto the. Oh no!
So
don't
one
do that.
question, we had a good question.
Yeah, sorry.
If there is an enantiomer, do you need to draw the enantiomer, or can you just say plus enantiomer? Both will be fine.
Okay.
This will both, as long as you know there is an enantiomer and it forms. Unless, like, I think on the last year's final, I had one question which was specifically like draw the mechanisms which lead to both enantiomers. You know, in this case, then I want to see that you know how it's forming exactly. You know, one is front side attack, one back side attack, or opening on the left carbon or right carbon, right? And then if it's a specific question like that, you might have to draw both. But normally, if I just ask for the products, you just put them there. You can say plus enantiomer, you can draw the enantiomer. Okay.
Okay, so that one will give you. No. I
Yeah,
keep
no double
doing that.
bond
Yep.
left. Yeah.
So this.
OH.
Or, not sure if this maybe is not the best way. I'm trying to figure out how to like because I know it's gonna still stick on there. Like,
That's fine.
wouldn't it kind of be
Yeah.
like underneath?
You can rotate it around the single bond in the end. But this is just fine. As long as you draw them both coming forward, that's what forms.
Okay, yeah. Is it okay if should I draw the second step? Because I know there's like this. Like,
What you can do,
like if it's like coming out of the board.
Yeah. So
I
what
just
you
gotta
can
try to
do
actually
is
draw
you
it.
can just do like this.
Okay.
Means, you know, we're going after
steps.
both steps, right?
Sorry.
Oh, sorry. So after both steps, we go here, and this is coming out of the board. This is going like this, right? And then put the OHs, so that'll be fine. And now this one, you see, this has two chirality centers here.
Is it OH or O?
Um,
On the bottom one.
oh, in the end, you need to get OH.
Yeah.
Absolutely. O alone doesn't. I mean, you can just if you have a single bond, just this one bond to an oxygen.
Yeah,
It's
that's
either
not-
negatively charged or it's a radical or it's either very unstable. So it's usually OH, right? All right. So we have OH here, And now here we have plus enantiomer because this is a chiral. Okay? Right? So this is very similar to the things I think you've done in lecture with bromine addition, and then that was anti-addition, and this is just syn addition. So, right, that's what happens. Question? What, you want to do the next one? Okay. So are you guys good with this one? Yes, question. The second,
Like this, if we drew out this,
yeah.
the first one, so what would that be for?
Oh, how would that look? Let me draw that, okay? I'll draw it for you. So we'll draw it separately. So you would get, if you do this, right? So this is both steps. Now if you draw it out, it will look like this. Now we have to do a ring. It's actually harder to draw because it's a ring. But let me draw it, okay? So it comes from the front. Like this, all right? And now, this is pointing up. The other one, methyl, is like this. And then there's a hydrogen here, and here's a hydrogen. Is that correct? What do you guys think? I think that's right. Does everybody agree, or did I make a mistake? This is, I think, what you get. Right? And then you see I rotated around the single bond a little bit. And then you go and you do the sodium bisulfide. Sodium 2SO3. Right? Okay. So actually it's easier, you see, to draw this thing, then you have to kind of rotate the single bond and rotate it back. It's almost harder than just going through both steps. Like in this case, as long as you kind of know the mechanism it's coming on syn, it's easier to draw it. All right? Let's go to the next one. Okay. Here we go.
Thank you.
Now these I don't remember from last year. These are a little bit harder ones now, which are coming up. As long as you know the solution. Okay, so what do we have? Upon catalytic hydrogenation.
Oh, catalytic hydrogenation. I totally did this wrong.
Okay, so it means catalytic hydrogenation over platinum it reacts with only one molar equivalent of H2. That tells you that there's one double bond.
I did this so wrong.
Tells you there's one double bond with the compound. Then A undergoes reaction with ozone followed by treatment EMF. That also tells you it's a double bond. To yield the symmetrical ketones. The double bond must be symmetric. And then you have this molecular formula. So that's the correct answer. Except B is
not
the
done
correct
yet.
structure.
Yeah, I did this wrong in my notes, so I don't know the answer to this one.
But what? So you are very, very close.
Mm-hmm.
You see B. So this is A. I remember even from blood. This is the correct thing. All right, A is correct. Does anybody have anything else for A?
Could you, what if you had the double bond on like one of the edges instead?
If you had the double bond on one of the edges,
Yeah.
then you would get a
Oh, okay, wait.
symmetrical diketone. Then it's not symmetrical. It's a little bit less.
Okay, no, I did do it right.
They're coming out from.
I did do it right.
on, like, either side there.
You mean like over here?
Yeah, like
It would be a
No, I
little
did
bit
it
less
right.
symmetrical.
it would be.
Yeah, it would be less symmetrical. It's not the best question because it would still be a little bit symmetrical. So I would still give you. It still has a mirror plane, so I would still give you credit for it.
I did get it right.
It's actually an alternative structure. But this, I think, means the highest possible symmetry. Exactly what was missing is just the diketone there. All right?
I
So
did it
you
right.
put it
I
in.
just thought I did
Okay.
it wrong. I got
No,
it
you got
this.
it right. The only thing is, you see the ketone, the angle. You remember what we once said? If you have a sp2 hybridized carbon, you draw it as a line drawing. If you draw it like this, you don't want to do it like this, right? You want to kind of put it like here. It just looks nicer.
In the middle of it?
Yeah, no, so what you can do, the way I would draw it is like this. you just draw these inside. It's just aesthetics, literally. It's not that huge of a deal. But you know when we talked about chapter 1, so I would draw it like this. Although yours almost looked nicer, to be really honest. So that's fine. That's not a major deal. All right?
Professor, could you explain how, like, the thought process behind this one? Like, especially for, like, the rings?
Yeah, the process, the thought process.
I wasn't sure where to start on this.
So you figure out it has one double bond. All right?
So, because 1 molar equivalent of H2, because all of these addition reactions are popping off the double
Yes.
bond.
So you need to, number one, okay, is you need to figure out how many rings there are, okay, and how many double bonds there are. So it's actually related. Part 1 of the problem is coming up with converting a molecular formula into line drawings, right? Kind of what we did way at the beginning of the semester. And how can you do this? There is a thing you can actually, if you have 10 carbons, what's the a hydrocarbon? For example, a linear chain with 10 carbons. I'll draw one. Okay, a decane, right? There'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many hydrogens you have on there? 22. Is that right?
22.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I think 21. No. 6 plus. Are you guys sure it's 22? Okay, I believe it.
22, yeah.
Okay, it's fine. It's hard to count. Okay, so 22. Now, how many hydrogens we have there in the compound? 16. Okay. Now, what happens when you take a hydrocarbon and you introduce a double bond? You have 2 fewer hydrogens, right? Because you basically do the reverse of a hydrogenation, a dehydrogenation kind. Okay. So whenever you introduce a double bond, you lose 2 hydrogens compared to the maximum number of hydrogens you can have. And then people call this an unsaturation. Okay, so they have one unsaturation. You might have talked about it, you might not have, but that's essentially what it is, the thought process. Now, how many unsaturations do we have here? How many hydrogens do we lose? 3. Because we have 6 hydrogens which are kind of missing compared to the maximum number you could ever have with 10 carbons. So that means there's only one double bond because it only reacts with 1 molar equivalent of H2, right? So that means the other way you can lose a hydrogen is by closing up a ring. Whenever you close a ring, you get rid of 2 hydrogens and make a carbon-carbon bond instead, all right? So that's another way you can introduce unsaturation. And so that means there must be 2 rings in there. And you see we have 2 rings in that A. So now you know there must be two symmetrical rings because it says it's a symmetrical compound. So the question is, how can you make 2 rings which are symmetric? And that's the way.
Okay.
Right? Does it make sense? That's kind of the thought process. So you're thinking that, yeah, Isaac.
Does compound A have to be symmetrical or just compound the diagonal?
Well,
the product has to be symmetrical. That's what the question says. But if you make something really asymmetrical to start with, then the product is very likely also not going to be symmetrical. There might be other solutions possible. And on the next exam, if there is other solutions, then they will be counted as correct. All right. So some of it is trial and error, like trying different things. Some of it is trying to figure out, how many unsaturations, how many rings you have, how many double bonds you have, what happens in the ozonolysis and stuff like that. All right, Caroline.
So sorry, last question. So how would you look at 1 molar equivalent of H2 and go, okay, that means double bond?
Because we know hydrogenation, right?
Yeah.
So if you know catalytic hydrogenation, it means you take 1.
Yes.
Like H2, you put it on the double bond, right? And then you hydrogenate. So if you had 2 double bonds, it would react with 2 molar equivalents of H2. Does it make sense?
Yeah.
Because each double bond picks up 1 H2, right? And then one of the hydrogens goes to one carbon, the other goes to the other carbon, you do hydrogenation. That's fine. So you see these kind of questions, they are heavily integrated. So if you have, this is the typical challenge question. All right, they won't be all like this on the final, but there might be some of it. Because you see, it combines the things from earlier chapters, like, converting molecular formulas into line drawings, right? And doing that relatively quickly is just a sub-part of the problem. Then you need to know all these reactions. If you don't, if you're not super familiar then with hydrogenation, you're not going to figure out it has one double bond, right? So it's a heavily integrated problem, which makes it a little bit harder. Okay? Question?
What do you know that it would be a cyclopentane?
A cyclopentane. So let's see. Let's try one, okay? So if we go, because you need 10 carbons, right? Mm-hmm. So you do this, for instance, as you do this, right? Then you have to make this bigger because you need 10 carbons. You need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, you could do this. And now if you cut it, it's less symmetrical.
Okay. What if you did like 2 pentanes next to each other and then like a double bond in between them?
Can you try to draw it?
Sure.
So this is less symmetrical, that's why.
Yeah.
It still is somewhat symmetrical, so it's...
Okay.
See if you can draw it.
All right. Like that. Would that
It's
not
the
work?
same number, but I don't know.
Would that not work because of
What
it'd
would
be
you
linear?
get? You would no. You would get this would break into 2, right? So if you do ozonolysis,
Yeah.
if you do ozonolysis, so 1, 2, what happens? You would get 2 equivalents. Oops, sorry.
Yeah.
You see, you would get 2 equivalents of this.
Yeah.
Now, is this a diketone?
No.
No, it's a monoketone.
Yeah.
You see, because a diketone has 2 ketone groups. That's why.
Yeah.
Otherwise, it's a great idea. But you see, then it conflicts with one little thing somewhere because it's a monoketone and not a diketone.
Yeah.
So that's why it can't be that one.
Okay.
Okay? It's a good idea. So you need to think through this, right? You need to think through, try out different possibilities. Okay? So we'll take this out, we'll take this out, we'll take this whole thing out. Okay? All right, so let's go to the next problem. Is that okay?
Yeah.
I think that helps to talk about the thought process a little bit. Now synthesis, okay? Synthesis, how do you do this? Go from there to there. It's a good question. I have no idea. Who has an idea? Okay, let's try. I'll look at it for a while, I might figure it out.
Oof, oof, oof. Let me see. So I think this is going to be an acid catalyzed hydration.
One key piece of advice for these kind of problems, okay? Because if it's just a one-step problem, for example, I ask for reagent, I give you the starting material and product, it's fairly easy because you just need to remember the reaction. You will see it. Once it's like 3 steps in between, it gets much more variable, but you get a lot of possible combinations. And to find the best one, you should think about it forward and backward. But thinking about it backwards is sometimes even more helpful than forward. So you think about it both ways. And then you get somewhere in the middle and you find the connecting step.
Yeah.
So let's see. So
I figured these are like the things that are changing.
Yes.
So I would say.
And you probably want to go through a double bond.
Yeah.
Because what are the reactions we have mostly talked about are eliminations and additions. Okay? So if something is changing, you wanna always kind of work with maybe making a double bond or adding something a double bond and then doing okay?
I was thinking.
So where would the double bond go?
The
Between
double
which
bond
carbons?
would go on here.
There, yeah. Okay.
So you need to
want to go. Maybe we want to make a double bond first. You see what I mean? You need to come up with an overall strategy. So you can make a double bond here, right? By eliminating.
Yeah.
Do an E2 elimination. You get a double bond here. That's the strategy, and then you add something to the double bond. What do we need to add? Water. But you add water to the double bond, and then you get to this. And you need to add water, then you can think about it. What's the best way to add it, right? We have 3 different ways. You can do it Markovnikov or anti-Markovnikov. But you see, then that's the way you do it. You go through the double bond.
Yeah.
That because we talked about chapter 7 and 8, okay? Like once you are in the spring semester, you will know like 50 or 60 different reactions, okay? You know what I mean? Then it's not so clear that you should go for a double bond. For now, in many instances, you go for a double bond. Okay? So try. So OH minus will not add to a double bond. Unless we didn't learn a reaction which adds OH minus. You need to,
So it's like a third step with the. So you it's like H2O, then you have to take the extra hydrogen off. Yeah. So first it would be one. So not the double bond here.
No. Yeah, so draw the double bond intermediate first. Let's go from. So we know we want to put the double bond. Let's do step 1. All right. What are we doing? We're doing an E2 elimination. So what would the reagents be for that one? We need a strong base. Anybody can help?
Oh.
Hydroxide, let's see. Hydroxide, would give half the points. Why? Because remember, hydroxide is a strong base, but it's also a good nucleophile. So if you use hydroxide, what will happen, and you see this is a primary carbon. So if you use hydroxide, it might give you like 50-50 of the SN2 product and 50-50 and the E2 product. And you don't want a lot of the SN2 product. So how can you avoid getting any SN2 product? You take a base, which is only a base, but it's not a nucleophile, or a very bad nucleophile. So some sterically hindered thing. One thing we learned is LDA, like lithium diisopropylamide, or sodium hydride is just a good base. But you know, from that reagent table we talked about, you want the reagent which is a good, strong base, but a weak nucleophile.
It would be something like.
Or T-butoxide. T-butoxide is the standard example.
Like that one?
That one, exactly. T-butoxide. Just use T-butoxide. I always use T-butoxide. It's fine. I'm not going to test whether you know 50 different bases. I mean, it's not a synonym kind of thing. As long as you know you use T-butoxide. All right? All right, so that's the SN2. No.
No, oh, it's the electron.
I just wanted to say you don't have to draw the mechanism, but maybe we should draw the mechanism. SN2.
Didn't really hit it. It's going from the double bond.
I will show you. Okay, just recalling the E2 mechanism, right? Be careful, guys, okay? You need to know these. This, very different. It's fine. Okay? You can take the heat a little bit, right?
Yeah.
You're fine. I'm just being tough on you. But okay, make sure, because now we talked about additions, you need to be absolutely like E2, SN2, SN1, all this stuff, anti-periplanar, all these things we talked about in chapter 7. They're going to come right back on the exam, okay? The exam is not just chapter 8. It will be a bunch of chapter 7 and chapter 8 plus all the other chapters, but heavy focus on 7 and 8. And the two chapters are linked together, particularly in the synthesis stuff. So make sure you review and relearn the whole chapter 7 as well, okay? Because frankly speaking, in my opinion, chapter 7 is harder than chapter 8.
Yeah.
Actually. And if you look at other textbooks, some of the McMurray textbooks, some of you guys have seen, they do the addition first and then the elimination, okay? So some textbooks do the other way around. Chapter 8 first and then chapter 7. Because chapter 8, I think, is actually a little bit easier. So make sure you practice that stuff again. All right, so here we are, and now we can go to the last step. So what we do, very simple thinking. What are we adding? You see, we have a H and an OH. That's what we are adding. So we are adding water. Now, there's 3 different ways we can add water.
You do the simplest one because it would be going on to the more substituted carbon.
Well, that's the question. Not the same. If you do the simplest way we could do is H plus, like H2SO4 and water. What will happen? Then you probably get a rearrangement. Then you can get you get a carbocation, and then you get a rearrangement, and then you would get something different.
So you need the BA.
So that's no good. That will give you a rearrangement.
BTHF.
Yes. But first of all, is it Markovnikov or anti-Markovnikov addition we want? Markovnikov, right? So this one would have been Markovnikov, the H plus H2SO4, H2O. But then it gives rearrangement, so we don't want that, okay? So that's bad. This was supposed to be a man, put this back, or some sort of smiley face. Sorry.
Can you draw out what the other rearrangement would look like?
I can do that. Let me see what, so if you did this, right, I'm gonna just draw this out for you guys. So if you did this, and you did H plus, all right, then what you get the carbocation here, okay, right, you get the carbocation there. Now the rearrangement, this would very, very likely, we have seen this before, would do probably like a hydride shift like this. And so you get a more stable tertiary carbocation, which then looks like this, okay? And then if you had water, the water would then attack that carbocation, and you would get a different product. It's not like you don't get a product, it's just you don't get the product you want. Does that make sense?
Yeah.
So, and then you would do, then you would do deprotonation, and then finally you would get this product, which looks pretty similar to what we want, but the OH is in the wrong position.
Yeah.
Okay, so that's what will happen. So we don't want that whole thing. So now, what's the other option? That's the boron thing. It would give you the anti-Markovnikov. So that's also no good. So the other one is the mercuration, demercuration, right? That's the one we want to use because it doesn't give you a rearrangement. So what again are the conditions? Mercury acetate, right?
Yes.
So then you need to write those conditions. So that's 1 mercury acetate, 2. What's the 2? That's the like a reducing agent. Sodium borohydride, NaBH4 in water. So the water needs to be at the first step, actually, not the second step, right? Remember? Because the water adds when you add the mercury cation adds first, then the water makes this 3-membered ring with the mercury, and then the water opens it up. So if you don't have water in the first step, that's bad, right? You need to write the water there. Does that make sense? Okay. Any questions?
Could you show what would happen if you did the sorry, these are the hydroboration oxidation?
Oh, so what would happen, guys? What would happen if you did the hydroboration oxidation? I'm not going to draw the whole thing, but what would happen is the OH would end up here, and the H would end up here. Does that make sense? It would be an anti-Markovnikov addition. You would put the OH onto the less substituted side in the end, and the H on the more substituted side with the boration.
I'm just kind of confused because both of those kind of make the triangle.
No.
No?
No. None of these make the triangle. The only one which makes a triangle as an intermediate is the mercuration. Because that one, the mercuration gives a triangle with the mercury.
Right there?
Oh, I see. So the way but that's just the mechanism we drew it. What happens actually? Yeah, in the lecture notes we
what's
drew
the difference
once.
between these two?
Oh, you see, yeah, I'll explain it. So when you do this bond between the boron and the hydrogen breaks, and it doesn't actually form a triangle.
Okay.
Does it make sense? Because you break that bond. You basically the boration, the boron addition with the hydrogen. What happens there is the hydrogen and the boron get attached to the two carbons at the exact same time. Okay? The only times you really form triangles, there's 3 times. One is when you do a halogenation. Okay? So you get a chloronium or a bromonium ion. That's the first case. The second case is the epoxidation, right? With the MCPBA. The peracids, okay, the oxygen triangle, and the third case is the mercury triangle. Okay, with just protonation, you don't get a triangle because the proton doesn't have another electron pair. With the borohydride addition, both just get transferred. And I know in the lecture notes, that's why you're confused. In the lecture notes, I drew it as resonance structures to explain to you which side, the boron gets kind of attacked a little bit first, and then the hydride moves. But that could make you think that you form a triangle. But you break the boron-hydrogen bond when the hydrogen attacks, and so it doesn't actually ever form a triangle.
Could you please show
Okay.
what would happen if you did that?
You mean with the boron,
Yeah,
the
like
boron
in
thing?
this example.
Okay, 1 second. So if you did this, all right, we're almost done. We will get there. So I'll take off this stuff on the left here, all right? So we get a little bit of space. Okay. So let's do it with this example and the boron thing, right? So if we did BH3, look, let me just draw it again, sorry. So we get a little bit of space, okay? So we're gonna put the boron over here. So which side does the boron go on to? The boron goes like this, all right? So you see the boron aligns. So the boron is the Lewis acid.
Sterically hindered that it goes on to the end, or?
Yes, it's for 2 reasons. Guys, listen for a sec. This is actually important. So we want to make sure that, you know, why does the boron go on the side with the less substituted side? Because this is the arrow pushing. You see, the boron is the electrophile. Okay, so the double bond attacks the empty orbital on the boron, and now this hydrogen moves over. Right? I drew it as 2 resonance structures once in lecture just to explain it to you a little, but this is what happens. That's the real arrow pushing, is both arrows at the same time. That's why you get syn addition. Everything happens at the same time. Now, why does this, you see this doesn't form a triangle? Because I know it looks similar to so in the mercury case, right? Very similar, but in the mercury case, we had a lone pair on the mercury which did the second arrow. In the bromine case, we had a bromine here, right? Another bromine here. The first bromine had another lone pair, and that lone pair would attack. But here it's not a lone pair. Here it's the boron-hydrogen bond, which does the attack, the second thing. And so that breaks this bond. So what we get is just a bond between a boron and a carbon here, and another bond between a hydrogen and a carbon. But we do not get a triangle, you see, because this bond breaks. Does that make sense? So we can talk more of that. But think about it overnight. We can talk tomorrow, okay? But does that make sense? You see, that's different. Because in one case it's a lone pair, in one case it attacks like this, okay? So I think we are good with this problem, okay? Who wants an apple? Give you an apple, okay? You did a good job here. So we do the next one. Who wants to try this one? Again, we must be going through a double bond, right? Otherwise it doesn't work. Bless you. Any thoughts? 2 more, right? We have this and then 1 more. Or do we have 4? No, we have 2.
No, it's 3 reactions.
3 reactions.
So we have
one of
more
them
after
we already
this.
did.
Yeah, 1 more after this.
1 more after this, okay.
We said 1 a lot.
It's okay. I thought we were going to finish this problem in like
Said 1.
15 minutes, but probably not.
Just not happening there.
Okay. See, this is a tricky one because we have to move the obviously, you see, you need to analyze it, right? So you see there's 2 methyl groups right on 1 carbon here, and now actually somewhat magically 1 methyl group now has moved over. There's literally 1 exact reaction we have ever learned which can move a methyl group. And what's that? It's a methyl shift. So we have to go through a carbocation which does a methyl shift.
I know.
Okay. Let's see what you're getting out of here. So you do the HBr. That protonates it, yes. So, let's see.
I know, like, the methyl shift. I don't know how that happens. Like, because then my next thing goes to...
So the best thing to do in this case is draw it stepwise.
Okay.
You are actually right. In very rare instances, the methyl shift can happen together with other things.
Yeah.
But you haven't really learned that, so the safest way to do it is just you draw the cation.
Yeah.
All right? And frankly, in all honesty, I think the easier thing to do, rather than putting a bromine there directly, is do it in 2 separate steps. All right? So step 1 would just be make the double bond and have the methyl shift.
Okay.
Okay? And then step 2 is the bromine addition.
Okay.
Okay, so basically you just want to do an elimination. Okay, number one. So but then you can just use H2SO4. Okay, to do the protonation. Just concentrated H2SO4. Okay, and then that will do the protonation. That gives you this thing. Now what happens next is you just literally have water is leaving.
Yeah.
Water is leaving.
And then get a positive charge.
And then you get the positive charge, right?
And a methyl shift.
And then you get the methyl shift. Right, like this.
So why the...
And then what? Let's see, let's try it. So then you get the methyl shift. So you get a new carbocation, which looks like this. Right, and here you have a hydrogen. And now you get the double bond. So how do we get the double bond? You basically you have the HSO4 minus, right, which is the base. And that will now deprotonate the thing. It basically do an elimination.
Mm-hmm.
So this is kind of, yeah. Okay, that's basically, it's just an E2 elimination. Sorry, E1 elimination, right?
Why did you choose H2SO4 to begin with instead of like hydrogen bromine?
That's a good question. Why do we pick H2SO4 instead of HBr? Very good question. If you'd pick HBr, Br minus is a pretty good nucleophile. So then what's going to happen with Br minus is literally you're going to get some addition of the Br minus to go here. So you're going to get a Br minus here, then you're going to get an alkyl bromide. And that wouldn't be the end of the world. So if that happens to you, and that goes there, then you can take t-butoxide, do an E2 elimination, make the double bond, and then add bromine, right? That's an alternative way. This way, I think, it saves one step. Okay? So you see with H2SO4, the HSO4 minus is a bad nucleophile. So it does not do this kind of, it does not act as a nucleophile. It will just literally just eliminate. Okay. That's the specialty. That's why people use H2SO4. And so that eliminates, and that gives us this thing. Okay, and then the last step, you see, that's just an anti-addition of bromine. Does that make sense? So, and that just goes through the bromonium ion. Okay, Br2, anti-addition. And that gives us the product. Do you guys have any questions? These are fairly difficult problems, okay? Okay. I'll bring you an apple. I think I have one more apple left after this, so one more person for one more problem. Thank you. This is great. But you see that you could do the Br, you could make the alkyl bromide and then do an elimination. That's perfectly fine. So the good news is for these synthesis problems, okay, there often are multiple solutions, and as long as you come up with something reasonable, which doesn't have a huge, clear problem in them, right, then it's fine. Okay? It's not just one solution. Okay, last one. Who wants to try the very last problem of the very last review session? And get the very last apple of the season? Isaac. Try. I'll get the apple. Just explain a little bit what you're doing. What are you going to do? Let's take a look. We talk it through first.
At first, so if you want to put a methoxide on at the end,
yeah.
Could you use catalytic hydrogenation, or would that not get rid of that double bond in the way that you want to?
So if you so if you get rid of the double bond,
yeah.
You see, so let me circle a little bit in yellow so that people can see what we're talking about. Okay, so you see, essentially what we are doing is we are trying to transpose the double bond. You see, we have a double bond here.
Yeah, and you want to send.
So if you do a hydrogenation, it's going to add two hydrogens, and you don't have any functional groups left to do anything anymore.
Okay.
You see then, because if you have hydrogens there, you can't do elimination or anything. So you have a hard time getting to this product.
Yeah.
Okay? At least with the reactions you know.
Yeah.
So another thing you can do, what if we, I'll give you some ideas, okay? So what if we, for instance, did an HBr addition first? You see?
Yeah.
That would then put a bromine in this position. And the hydrogen over here. Okay, let me draw that.
And then do an elimination.
We can kind of do it together. Then do another elimination. That's
Okay,
right.
all right.
So, you see, but you do an elimination in a way so that you then make a double bond across here.
Yeah.
And then you do finally an addition
And then
again
it's-
of methanol, right, with H3O plus and methanol. Does
So-
that make sense? That
so
will do it.
Could you do HCl as well, or
You could do HCl as well. That's almost equivalent. That will work. So can you draw it out? That would be the strategy I would probably recommend.
okay?
Does that make sense? So draw the whole thing out. You don't have to draw all the steps, right? Just
Yeah.
I mean, all the mechanism steps. That's the other thing. Like if I'm asking you just figure out reactions and synthesis, you don't need to do the whole mechanism. Okay? You have to think about it to make sure you know what you're doing. But unless I'm asking for the mechanism, you don't have to draw the whole mechanism every time. Okay?
And then to
It'll save you time.
get rid of the Br,
Okay, so what do we do? What's chapter 7? Elimination. And then there is two types. You can use a large base, or so we want to probably do an E2 elimination.
right?
But
Okay.
then what kind of base do you use? A small base or a large
steric,
base?
a big
Hoffman
base.
product Versus,
So,
what is it? Hoffman versus.
you do a small one because actually, will it
It
matter?
gives the Zaitsev product.
Yeah, that'll give us the Zaitsev. So
That's
like
right. That's right.
methoxide is in, but now that's not going to get it. That's going to.
Well, is methoxide going to do an SN2 reaction?
Okay, okay.
No. No.
What about,
no, it's not going to do an SN2 reaction because it's tertiary.
Yeah.
So you cannot do, you can never do it. Remember, we said you can never do an SN2 reaction with a tertiary substrate.
That's
so
right.
You can use a small base like methoxide. It's great.
Okay.
Because it won't do an SN2 reaction in this case, right? Because it's tertiary substrate. Does that make sense?
I can't. It's like I forgot all the chapter 7.
Well, I'm sure you're not the only one. That's why before I gave this very motivating speech. I mean, it's not the end of it. You knew it once.
Yeah,
See,
yeah,
here's
yeah.
the good news. If you were once pretty good with chapter 7, like 3 weeks ago before Thanksgiving, you know, it's going to take you like a day or two and you're going to be up to speed again. Okay? It's not the end of the world. That's why we're doing this now. It's only Thursday. You have until Monday, or even Tuesday morning to study for the final. So what I'm saying is start to review chapter 7 now. It'll be great. Okay? The problem is, if people haven't, for example, studied chapter 7 yet for the midterm, but they haven't taken the midterm, then it can become difficult to pick it all up.
Because here you're going to take a hydrogen, right?
Yeah,
from
you take
here.
a hydrogen. That's right.
And then we'll go there, and then you get.
Yes.
and then
Yeah,
this
you got it.
leaves.
You
All right.
got it.
And so,
What was the reason that we had to use a small base instead of like a butte or something?
Yes, question. Why small base rather than a big base? The big base, like butoxide, would take the proton from the less hindered position because it can't reach the small position. And that's Hoffman, that gives you the so-called Hoffman product. And so that would just bring you back to the starting material. That wouldn't be the end of the world. You would get back to your original starting material, and then you could add HBr again, and then try a different base. But it would be kind of going around in circles. Okay? Does that make sense? That's why.
and then to,
So you want to make the Zaitsev product, not the Hoffman product. Yeah.
so we don't want to use methoxide because it's a bad, or it can do an SN2 on a secondary substrate.
Oh, but here we are not doing. Now you have to be careful
Okay.
for the last step, right? We're talking about the last step.
Yeah.
Last step now. What is it? It's an addition reaction.
Okay.
And we generally, with these double bonds, we need something electrophilic in there.
Okay.
Because remember, the double bond is a nucleophile.
Right.
You need an electrophile to react. So you can't just take methoxide. It won't react with the double bond. You need something acidic. So methoxide can come from methanol.
Yeah.
Right?
Yeah.
But then you need an H plus in there or something, which will do the protonation.
Okay. So just H plus in water. or H plus in
H plus in methanol.
in methanol?
But then
Okay.
but then it might give you also the wrong product. Let's see. Let's write that down. Let's see what we would get.
And then if I know the book says if you do it in a peroxide, it'll give it the anti-Markovnikov, and is that good enough?
Sorry?
The book said if you do this something in the presence of a peroxide, it'll put it on the anti-Markovnikov. Does that apply here? Because that would give us exactly what we wanted. Yeah.
Oh. Yeah, but you haven't learned that.
It was a paragraph in the chapter.
In the chapter, yeah, we didn't talk about it in lecture.
I think we might have. Was that like MC?
It was in, no, it was like, it was, I don't know, kind of in the beginning of chapter 8.
You would have to do it with a halogen or something.
Okay, so it wouldn't apply.
If you do like HBr,
We went over it. It was the MCPBA was like the example we used for the peroxide.
no, but we have other options.
Okay,
So this reaction you don't need to know, the anti-Markovnikov addition of HBr, because it's a radical mechanism. I didn't talk about it in lecture. I know the book has a paragraph about it, but I don't want to just teach you reactions you have no idea how the mechanism goes, okay? You'll learn about it later. It's a radical addition. It's just different. It gives you the anti-Markovnikov addition. No, but there's another way to do this. Let me show you.
okay.
Let me show you. I start to remember how we did it in the past. So the beginning is right. So we need to add a couple more steps. So there is one reaction you know which can do an anti-Markovnikov addition. And what's that? The borane. Okay? So you do the borane reaction. Let me show you. Because again, this won't work because this last step is going to give you the Markovnikov adduct. The methoxy is going to be on the tertiary carbon. And that's going to be the wrong thing. Okay? So that's no good. So we take that out. It was a good idea. It was worth a shot. But, you know, but we are almost there. All right? So what do we do? Sorry, I need to sit down so I can still talk. So what we're going to do is we use the reaction you know, which gives you an anti-Markovnikov addition. So it would be the borane, BH3, THF, right? And then number 2, H2O2, right? And then some base like sodium hydroxide. So then let's draw the product of that thing. And see if we can go from this product to the final thing we want. So here now, right, we get the hydrogen here. And, sorry, the OH over there. How can you go from an OH to an O methyl? You know a reaction which can do this. Any ideas? As an SN2 reaction, where the O minus is the nucleophile. So let me show you. All right. And we have a lot of steps here. So you basically use a base. You can use a base like T-butoxide, for instance, right? And what the base will do now is this. It will come in, deprotonate the alcohol, right? And you will get this thing. You would do this all in one step, right? I mean, but you would get the O minus. Are we getting elimination here as a side reaction? No. Why not? Exactly. Because it's an O. That's the answer. Because you're not getting E2 elimination here. Because OH would be the leaving group, OH minus, which is a terrible leaving group, right? That's why we are not getting elimination, so we don't have to worry about it. Does it make sense? Otherwise, you couldn't use T-butoxide, which is eliminate, if this were a bromine instead of an OH. All right? So far, so good, right? Now, the only question is, how do we go from here to here? You use something which has a methyl group, which is electrophilic, and so, for example, you put an iodine on there, or a bromine, right? And so that's a good substrate for a SN2 reaction, where the oxygen can actually attack here. Okay? Then you get the product. That works. With these reactions you have all learned. Okay? You can, if you know the reactions we haven't learned and they work, I will give you all the credit. Okay? But you will go through a lot of trouble. Like you basically, you have to learn all the new reactions we haven't learned yet. So I will make sure I'll give you problems on the final for synthesis, which you can solve with just the reactions you have learned in lecture. Because otherwise it's not fair if I'm asking reactions of you which you have never learned before. I think that's not the fairest thing. Okay? One more question and then we are done. Yeah.
When does the stereochemistry begin? Is it when you have that turd oxide?
Yes. Oh, that's the other question. Stereochemistry. I completely forgot about it. Is the stereochemistry correct here?
Yes, because that's in 2.
Yeah, the problem is the syn addition there.
What about the methyl? Methyl's playing there.
Yeah, it's a syn addition. You see? Look, here, right? Here you do a syn addition. That's the other hint at this problem. You do a syn addition here. For example, the boron comes from the back side, so that means the OH will be back. And here the H will also be back, right? So the stereochemistry at that step is this is pointing back and this is pointing back, right? And so that gives us the right, plus the enantiomer, right? So that gives us the right stereochemistry in the end. When you...
When does it come out? Oh, because the methyl group is going to come forward. Okay.
Methyl is forward, so that means H must be down, but the H is not drawn. Yeah. But you see H and OH, or OIME in the end, they're syn, which is correct with the stereochemistry of the reaction. Okay. You're absolutely right. We should think about that too. I just completely ignored it. But luckily it works out. Okay? Thank you, guys.